guys, welcome back. So this part is bar magnet and its properties. You must have played with the magnets in your childhood, and regarding properties, you must have done these properties in your junior classes. So only here we have to review these things that what you have already done, just we are reviewing to begin the chapter. So let us see that what are these. So guys, bar magnet and its properties. Now in the bar magnet, let us review once again the magnetism. Now magnetism, the phenomena of attracting magnetic substances like iron, nickel, cobalt, etc. is called the magnetism. Now if we look towards the next thing, that the body possessing the property of magnetism is called the magnet. Next thing, that is the magnetic pole is a point near the end of the magnet where the magnetism is concentrated. This we have to remember, that magnetic pole is a point where at the end where the magnetism is concentrated. This is what we have to understand. Okay. Now if we move towards the next thing, that is Earth is a natural magnet. This we're going to study more in details in the terrestrial magnetism in the coming part. After that, we have the region around a magnet in which it exerts force on other magnet, and on objects made of iron is a magnetic field. Although we're going to discuss this magnetic field part in the later part, but at this moment remember the definition, that the region around the magnet in which it exerts the forces on other magnet is called the magnetic field. Okay, now let's move towards the next slide. Now if we look towards, this is a bar magnet. Let's consider that this is a bar magnet. Now these are the point. This is the yellow dot, that is the P, or we call this as the north pole, and this is the south pole, SP, that is the south pole. So these yellow dots are the points. These are the points where all the magnetism is concentrated. So if we move further, that is this M shows the magnetic dipole moment. This dipole moment we'll discuss in the next part or in the coming part, so don't worry about that. So this is M, that is dipole moment. After that we have the magnetic length. What is a magnetic length? It is the distance between the two poles. Then after we have the geographic length. This is the complete length of the magnet. Now let's proceed towards what we have. Okay, a line joining the poles of the magnet is called the magnetic axis. Now if you look at this thing, look at the diagram. If I join the poles something like this will act as the magnetic axis. Now let's proceed further. Now if we talk about the next thing, that is the distance between the poles of the magnet is the magnetic length of the magnet. This we have already discussed, that the distance between the poles is the magnetic length. After that we have the distance between the ends of the magnet is called the geometric length of the magnet. This also we have already discussed, that this is the geographic length. After that, the ratio of the magnetic length and the geometrical length is nearly 0.84. As we can see from the figure, that geographic length is more than the magnetic length. Now let's proceed further. Now let's discuss the properties of the bar magnet. A freely suspended magnet aligns itself along the north-south direction. Okay, this we know. Okay, the next thing is the unlike poles attract and the like poles repel each other. This we have already discussed in the introduction part. Second thing, that is the magnetic poles always exist in pairs. Poles cannot be separated. Okay, although this is not a new thing. This is already being discussed in the introduction part, where it was treated as the monopoles cannot be, or the isolated monopoles does not exist. So this is the same thing. Now if we move further, the magnet can induce magnetism in other magnetic substances. It attracts the magnetic substances. Okay, so we have learned two things from here, that is magnet induced magnetism and it attracts magnetic substances. This we must have observed in our daily life. Okay. Next thing, let us look at the representation of a uniform magnetic field. Now, if we talk about the uniform magnetic field lines, so field lines are something like this. So we have to check it out, that what are these directions. That means if we talk about the first one, this first one, these are the lines. So these lines are represents as uniform field on the plane of the diagram. That means these lines are the direction of these lines are in the plane of the screen. If we talk about the second one, this is the uniform field perpendicular, these cross. These are the uniform field perpendicular and into the plane of the diagram. So that is, it is going far from me, or it is going into the screen. Now if you check out the next representation, that is again the same, third representation is left, that is third or the last representation, that is the dots. Now these dots are the uniform perpendicular or the emerging out of the plane of the diagram. That means these are coming towards me. So this is the last representation of the magnetic field. Now we have to check out the we have to remember the directions of these magnetic field. Okay, now let's move towards the examples. So in examples, in a bar magnet, magnetic power is A option, more at both ends of the magnet, more in the middle of the magnet, is same through the magnet, and none of these. Now we have seen in the diagram that this is the magnetic pole, this is the bar magnet. Now these are the poles, these are the poles, these are not at the ends, these are somewhat, these are near to the ends. Okay, if this is south pole, this is north pole. So what we said, what we have learned, that the at the poles the magnetism, all the magnetism is concentrated. So in the bar magnet, magnetic power more at both ends of the magnet. That means it will be more at these ends, both ends. So therefore, according to this, option A should be correct. Now let's proceed towards the next example. A bar magnet is immersed in the heap of iron filling and pulled out. The amount of iron filling clinging to the A option, north pole, is almost equal to the south pole. North pole is much more than the south pole. North pole is much less than the south pole. Magnet will be same all along its length. So we have seen in the previous example, or in this part, that at poles all the magnetism is concentrated. So therefore the magnet or the iron fillings which will be clinging, that will be north pole is almost equal to the south pole. That means iron filling clinging, amount of iron filling clinging to the north pole is almost equal to the south pole, because here is only the place where, or these are only the points where all the magnetism is concentrated. So guys, I hope that we are successful in reviewing this part, and also you have enjoyed this part. For the regarding the question, what do I hope, that you must have answered before me. So this is what do we believe. Okay, so we have the next part which is related to magnetic dipole, and for that upcoming part, stay tuned.